So again, Brandon Ross with Network Utility Force. Just a real quick on us. Network Utility Force is I'm going to skip using mic, but you can hear me up here, right? Pretty well. Network Utility Force is a professional services organization focusing on network infrastructure. So we do all kinds of network infrastructure projects, everything from building fiber networks to designing data centers, and in this case, of course, we're talking about IPv6. We partner pretty closely with Walker and Associates, and I'll be hanging out at their booth tomorrow, and then my colleague Tim Brown will be here as well. So if you have any follow-up questions we don't have time to talk about here, please come over to the Walker and Associates booth, and we'll be over there as well. And like Jim said, if you have any questions, please just stop me at any time. I'd love to focus our talks more directly on what subjects that you guys might want to talk about. So this is like a very small snippet of our much larger IPv6 training class. Our class is IPv6 Forum certified. So if you take our full class, you can take the IPv6 Forum certification test, and you can be an IPv6 Forum certified engineer. The full class can be anywhere from a day to 3 days, depending on how in-depth you want to get. We're not a big training company. We focus our training on specific organizations, so if you did want to do something like that, we would work with you to customize a class to your needs. So, just jumping into IPv6. So real quick, who here has any experience at all with IPv6? Good? Okay. All right. So some of this will probably be reviewed because this is a real quick version of it, and you'll see there's a lot of slides here because I pulled these from our training, so we're going to skip over a lot of stuff in the interest of time since it's only an hour, what generally takes a day. But a little bit of review then, IPv4, of course, is what we're all using today. It's the ubiquitous protocol across the internet. It's getting up there in age. 1978 was really when it was developed by ARPANET. But IPv6 is not really new either. We have about 20 years of at least some operational experience and a lot of experimental experience with IPv6. So, in the marketplace, we talk a lot with a lot of folks who see IPv6 as a new, untested protocol, but that's really not true. The whole protocol suite, at least the core parts of it, were done by like 1999. So we're still talking 17 years since the standard's been completed, and then networks started deploying it soon after that. The problem is we just haven't really had ubiquitous deployment, and that's mostly because of economic reasons. No reason to deploy a new protocol until you have to, right? Because there's cost associated with that. So why did we design this new protocol? What was the case for designing IPv6, right? Yes?
We we're running out of IPv4 addresses.
Yes, exactly. That's certainly the primary reason for deployment of IPv6 today. When we were redesigning the protocol, we were looking at, if we're going to have to deploy a whole new protocol anyway, what other improvements can we make to the protocol? And we should look at that as well. Yes?
Security.
Yes, security is one of them. And so, I think my next slide here, we'll get to that in a second. So security was certainly one of them. Simplifying the headers, making the protocol more efficient was another goal of the new protocol. But in the meantime, while we were running out of IP addresses, we did a number of things to make IPv4 last longer. Everybody probably remembers the old classical networking, the Class A, Class B, Class C, right? We got rid of that because that was wasteful to assign like a Class A network to a small organization, where Class B was never necessarily the right size either. So we did that. We made addresses more dynamic. First, back in the dial-up days, of course, with PVP, we could dynamically assign addresses so they were only in use when people were actually online. That saved a good amount of addresses. Today, really, a lot of the savings comes from NAT, though, by overloading and sharing addresses between multiple uses. Obviously, we get a lot more efficiency out of the address space. But to your point, we are still running out of address space. Here in North America, Aaron ran out of addresses from their free pool, which is the space that we can get more address space from, about a year ago. Now, addresses are still available for purchase on kind of an open marketplace, but that price is obviously going to go up as supply goes down. All right, so some of the goals, this was a chance to eliminate some of the complexity in the IP header. We'll talk a bit about that, not in excruciating detail, but at least some of the summary to it. We wanted to include more features around QoS, mobility, subjects like that have been included in the protocol. So, of course, what are the main features of IPv6? Obviously, the larger address space. We simplified the header format, and not just simplified it, but arranged it in a way that it would be more efficient for equipment to process. QoS was designed into IPv6 from day one. But we've also taken the same features in QoS that are IPv6 and backported them into IPv4 by using what used to be the class of service fields as div server. So we'll talk about that really briefly. So one of the things we talked about a little bit that you mentioned was this security was requiring IPsec support in the header. And so for the first few years of IPv6, this was an official requirement that IPsec for security be included as part of the IPv6 protocol. Unfortunately, at the time, because of the way that equipment and software was developing, this didn't really ever come true. While it was an official requirement in IPv6 for quite some time, a lot of the vendors still weren't able to implement it. A lot of times the excuse was because they had low-powered equipment that couldn't handle IPsec. So unfortunately, in recent years, we've kind of backed off of that requirement, and IPsec is actually no longer a required feature of IPv6, but is optional. It is, however, built into the header format, so we don't have to use separate IPsec headers like we did in IPv4, and we'll talk a little bit about that in a little while too. So, I like my cheat sheet here. These are the easy differences to spot between IPv4 and IPv6. So first of all, we talked about the much larger address space. At IPv4, we had a 32-bit address, right? We're used to seeing it in this format here, right? Dotted decimal with 8 octets separated by decimal. In IPv6, we've increased that address to 128 bits. 128 bits, that's 340 undecillion addresses. That's a huge, huge, huge number of addresses. People like to say there's more IPv6 addresses than there are grains of sand on every beach in the world or something like that. Now, the reality is that we do divide the address space up a little bit inefficiently so that we as humans can better read it. But still, the total number of addresses available is this giant number here. Another big change we made, and we'll talk about this in some detail too, is the format of the address, right? We just talked about how the dotted octet format here, the dotted decimal format here at IPv4 would not have worked well for IPv6. That address, if we wrote it the same way, would be as wide as a page. So instead of using decimal, we were using hexadecimal to represent the letters that are outside the address. And so we'll do a quick review of that and how that works, but the format is separated with colons to help differentiate when you're looking at it from an IPv4 address. We changed the header length to be fixed. Again, I made a couple comments so far about how the header format was simplified for easier and faster processing. A variable length header, at least in the 90s, was much more difficult for equipment to process because it always had to calculate where in the header particular bits of information would be. So the decision was made to standardize on a fixed length header instead of a variable length header, so that you know that a particular piece of information is always at the same offset, always at the same spot in that header every time you come to it. Some changes made to the minimum packet size. It used to be 576 bytes, but now we're up to 1280. This makes the protocol more efficient because more packets. Remember the burden of processing packets is in how many packets there are, not how big they are, right? We're looking at each header. Yes, sir.
Right. So, can IPv6 can you subnet it, and also can it be used dynamically like it is for IPv4? Now, although that is a ridiculous number, we thought that was a ridiculous number when we first came out with it. So, have they put in some kind of fail-safe for running out?
Yes. So right now we're only assigning out of a very, very small part of that address space. And so the standards that we have in place for IPv6 and how to use the address space, we're only assigning out of basically a block of addresses that's already as big as IPv4. Because remember how big IPv6 is, you can fit the IPv4 address space in IPv6 2 to the 64 times, right? So we're only even assigning addresses out of one block that's about the size of IPv4. If we run out of space in that block, we'll know that we're probably doing something wrong, and we can change the standards of how we define it. But the bottom line is that even though most of the large service providers already have pretty big chunks of IPv6 space, if you looked at it on a pie chart, you wouldn't even see the line of how much address space has already been assigned out of IPv6. Yeah.
Two questions. First question, minimum packet size is now larger. That sounds to me kind of like we're taking away options, and it's going to make packets that could have been tiny unnecessarily large. For instance, ping packets are now going to take up like 2.5 times as much space as necessary.
It's true, but remember bandwidths are a lot faster these days too, right? So back in the days when we had 576 bytes, we designed that for dial-up lines that were down at, maybe even as low as 1200 baud, or even 300 baud if we go back far enough. But really in the more populous times, more like 56K was really kind of our standard speed, right, in the 90s at least. Now, if you have a connection to the internet less than 10 meg, you're probably pulling your hair out about how slow things are working, right? So with so much more bandwidth available, a slightly larger packet size is only maybe about 3 times larger, not even. It's really, really kind of at loss of the noise. So.
Okay. Yeah. And then the other question I had is, obviously we've seriously crushed the virtual address space. We've got tons of address space, but with physical devices, we're still limited with the number of MAC addresses. If we're adding IP addresses to every single little device, like refrigerators,
yes.
Watches, all that sort of stuff. So I guess my question might be a tangent, but are we looking at doing a new standard for physical addresses as well, so we don't start running out of those?
So no, well at least not as far as I know. So that would be, so remember the physical MAC address for Ethernet are managed by the IEEE, okay. While IPv6 addresses are managed by NETUF. So of course they talk to each other, but they're very different organizations and they're very different standards process. As far as how many MAC addresses you can put on a particular Ethernet segment though, for example, and we'll talk about this a little bit when we talk about the specifics of addressing, but by standard, all LANs in IPv6 are defined to be as /64, so 64 bits of host address. With 64 bits of host address compared to only 48 bits of Ethernet MAC address, you can take every Ethernet MAC that's ever been created and put it all in one LAN. Not that that would work really well, but as far as the scaling of the address space, we're fine. So on any particular network, there's no real limitation as far as addresses goes and how many devices we can put on it. There's still performance and management and other reasons you want to split it up, but as far as the addresses goes, it gives us kind of ultimate flexibility.
Got it. Okay.
Yeah, but as far as IEEE, I don't know if there's been any concern or work over whether we're going to run out of MAC addresses. But keep in mind, with MAC addresses, we don't need to aggregate those. In IP addresses, we need to be able to make sure that address space is aggregatable because of routing, right? Because we wouldn't want a routing table with a separate entry for every single Ethernet link and every single Ethernet device in it. It would be unscalable. We'd never be able to store that many addresses. So for IP, we want to make sure that's aggregatable into a single route for a large number of devices. So you can't necessarily assign IP addresses sequentially, but you can for MAC addresses because you have to guarantee that they're unique on a particular LAN, but they don't have to be routable. You don't have to know halfway around the world how to get to a MAC address.
And even if they're not unique on the same LAN, you can actually separate it to an NAC or something. You can take it away from each other and make sure that it's unique. So you have the same MAC address on 30 different computers.
Oh, okay.
It doesn't matter because your router and all IPv6 will take care of where it's going. It doesn't matter.
Yeah, as long as you put them in separate broadcast domains, then you would be fine. Even if you duplicate the MAC address. All right. Sure. We'll talk a little bit about this flow field, packet flow label field. That's kind of interesting in a new development and how we might use that going forward too. And that's the other major difference. Oh, and then header options we'll talk about at least as well. We don't have any option field left in the header anymore now. We use these header extensions. Header chaining is what it's called, and we'll have to talk about that a little bit too. So we talked about most of this. Things to get used to in IPv6 though that you may not be used to in IPv4 is multiple addresses per interface. You may be used to that a little bit on a router if you had multiple subnets on a particular interface, but in IPv6 it's entirely normal and expected for almost every interface to have more than one address. At very least, you'll have a link local address, which is used just for local communication on that particular broadcast domain. But also, on top of that, you'll usually have a global unique address, at least if you're using that interface to reach the global internet. So there's 2 already. There's a bunch of other kinds of addresses that we might get into and we might see on an interface. But suffice it to say, when you're designing an IPv6 network or troubleshooting and you look at an interface and see that there's 5, 6, 7, 8 addresses on it, that's not something wrong, that's not unusual, that's expected. We're restoring end-to-end connectivity, right? We mentioned NAT was kind of the major way today that we're conserving addresses. Well, NAT breaks the end-to-end connectivity model. What's the end-to-end connectivity model? That means that a packet coming from my device over here will be transited across the network unchanged and reach the device it's addressed for. NAT, of course, has to process that packet, change addresses, sometimes do some other stuff to the packet in order to transit that packet across the network. And that breaks that end-to-end principle. When there's only one NAT in the way, we've created various hacks in order to make connectivity work across those. But as we have to use more and more NAT to conserve more and more IPv4 address space, we'll see paths of 2, 3, 4 NATs in the same path. And once you do that, that end-to-end connectivity breaks entirely. And that means that all of our data ends up having to go through some sort of central point, some sort of server somewhere, which obviously is less efficient. So by moving to IPv6, there's no NAT in IPv6, at least not standardized. So we're hoping that we're moving back to this end-to-end connectivity model where any device on the internet can talk directly to any other device as long as security policies allow that. Upper protocols are unchanged. So everything you know about TCP, everything you know about UDP, about ICMP, about ping, about all those kind of things, it's all the same. ICMP, of course, has changed a little bit for the actual parts that manage the protocol for bootstrapping, but for TCP and UDP and all that stuff, it's exactly the same. So the three-way handshake you're used to in TCP, the only difference is now we're wrapping that packet in an IPv6 header instead of an IPv4 header. So you're not losing any knowledge there. This is the whole model of layers within the network. It's only that layer that's changing when we deploy IPv6. All right, so I'll talk a little bit about packet structure. Pretty simple. We have this IPv6 header now instead of the IPv4 header that might have been there before. Remember, this is now a fixed length header. So when we did need to use some sort of options like, it could be IPsec, it could be a source routing header or something like that, instead we're adding these extension headers on instead. So this is always fixed, and then we have these extension headers, and then we have the rest of the packet. And the rest of the packet, again, is unchanged. That could be TCP or UDP. Here's a easier side-by-side comparison of what that looks like. You can see that we did remove some fields. There's no more header checksum, for example. The reasoning behind removing the checksum was that almost all of our lower layer protocols, which are almost always Ethernet these days, already have checksum built in. So why are we duplicating that functionality by putting the header? So we took that out. We changed, for example, the total length to just the length of the payload. Like we said, we have a fixed length header now. So we don't need to include the header in the length of the packet. We used to have a protocol field that would tell you what the protocol is coming next, but now that we have this header chaining concept, which again we'll talk about here in a second, we now have a next header field that tells whatever's processing the packet what to expect next in that device. And then one of my favorite changes is TTL is now hop limit. Now who, when they were first learning IPv4, saw the field time to live and thought that was like in seconds? I know I did. I always thought it was, for the longest time I thought it was in seconds didn't make any sense, but it's not. It's just decremented every time we route a packet, right? So all we've done, the field works exactly the same. All we've done is recognize that this isn't time, this is the number of hops. And so it's now called the hop limit field. But the concept is the same, and so it prevents loops the same way that you're used to. So we call this added fields traffic class. That's really diffserv, which is what we did by modifying the use of the type of service fields. Remember the old type of service fields, like secret, top secret, that sort of stuff, which we never really used, or certainly haven't used in recent history. So that works the same as it does in diffserv and IPv4. And of course, we've expanded the 32-bit address to 120 bits. And we'll talk about that flow label just a little bit. All right, so we talked about most of this. No option field. We're using these extension headers now. That means that the header is now always fixed length, is always fixed 40 bytes. No more cross, no more checksum. And this is important too, and we'll talk about this in some detail, is that you're no longer permitted to fragment an IPv6 packet along the path. You can fragment at the source if necessary, but along the path, we've eliminated fragmentation. The reason for that is to improve performance across the network and reduce processing across the network. By fragmenting a packet in a particular router, that router would have to take that packet, figure out how many pieces to split it into, create new headers, and there's always a lot more processing to it. So it's more efficient by forcing the network to not allow that. However, that creates some side effects that we need to be aware of, and we'll talk about it a little bit. All right, so we talked about this header chaining concept. So this is it, and it's really this simple. So your typical packet that doesn't have any special extension headers just looks like this. You have your IPv6 header. Let's say this is a TCP packet. The next header field type is 6, which corresponds to TCP, and then you have your TCP segment. That's it. 99.99% of packets you'd ever see in IPv6 will look just like this. Or it might be, say, UDP or something like that. But let's say we needed to add a routing header. We wanted to do some sort of source routing. We wanted to use an option for source routing. Instead of lengthening the packet header like we did in IPv4, instead we tack on a routing header extension packet. And the way that works is we tell we tell the processing, whether it's a router or a firewall or switch or whatever, that the next header is going to be type 43, which means a routing header. So if I'm a router and I see the next header type is 43, I know, hey, this next header is probably going to be important to me, and I can hunt that packet up to a part of the code that's going to process that extension header. But let's say I'm some other device that doesn't care about routing headers. I see it's type 43, I know I can just ignore that and forward the packet on. So that's the whole idea. And this, because there's a whole bunch of these that are undefined, that gives us these options to create new extension headers in the future for functionality that we haven't invented yet. Yeah.
How many bits is that again? That field? Next header?
Good question. Next header field looks like
Oh, it's
8 bytes.
Oh.
8 bits.
Oh, wow. All right.
Yeah. So lots of room for expansion there. And then we could chain multiples of these at the same time, right? So let's say that we want a routing header, but we also want to do IPsec in the same packet. And that looks like this. We just have the fixed length header next 43, right? That refers to the routing header. Now the routing header has a next header type of 51, which indicates the next extension header will be an authentication header, an IPsec authentication header, and then the TCP segment after that type 6, right? So now for a firewall, the firewall might look at that and go, okay, well I know I need to look at the routing header. Oh, next type is 51. I also want to look at the authentication header so I can process this packet as an IPsec tunnel, perhaps. Now, this is a pretty interesting concept. I think it gives us a lot of expandability in the protocol. However, there's some problems with it too. Problem being that every time you use a next header type that has to be processed in a higher layer, you're queuing that packet to go to some other part of the code, and you can use that as a denial of service attack. You can use that to go and shove packets into part of the processor and either fill it up or use all the resources of a particular device. So there's some debate in the internet about what types of extension headers we should be using, whether they should be allowed in all places.
And you're also kind of, like, from a conceptual point of view, you're cramming a lot of layers into one layer, and very dynamically putting layers in. We're still talking layer 3.
Yeah, so most of the extension headers focus around layer 3 concepts for IPsec, which you can kind of debate where that really fits. But the various, I think I took the slide out that showed all the different types, yeah, just in the interest of time. But most of them deal with either routing or some sort of per hop processing. So it's not too bad. But you can easily imagine creating new extension headers that do all kinds of crazy stuff.
So you can't create your own, right?
Well, I guess in theory you could. It wouldn't be standard unless you put it through the ITF process. But yeah, I mean, nothing really stops you. But nothing really stops you from doing that kind of stuff in IPv4 either.
I thought there was only like 5 or 6 extension headers. Like you said, I think you can create your own, but I think you have to go. Well, I understood it right. You have to go to Diana to standardize.
So yeah, so to get an extension header number, that would go through IAM. To create the standard itself, I mean, the internet's an open standards kind of process anyway. Anybody can write an RFC and submit it to the right working group, and if they all agree that it's good, then it gets passed.
There's also an order, I know, and I'm not myself quite clear. The order of them, like normally you see the extension header and the IPsec, there's extension header.
Well, there's routing headers, there's IPsec, there's security headers, there's a few other types. But yes, you're correct in that. I think what you're saying is that there's a particular order that the extension headers have to go in. And if you think about why, that makes sense, right? You would want, you're going to want your routing header to always come before a security header, right? Because it's more likely that the router is going to process the packet first. So there are rules for what order the extension headers need to go.
I'm sorry, but I guess my point is that it's not as easy as you think. Just create your own.
No, it's not.
Extension header and
Right.
expect it to work, because there are, even though it sounds open, it's not as open. At least I don't think it's as open as the first time you mentioned.
Right. That's right. So that there's rules about how the extension headers need to be processed. It's practically it's not really practical to create your own extension headers. If you have a need that the whole internet needs, chances are you can go through the standards process and get it approved, but that's a long process. You doing something just for local use, probably not useful. But in theory, I suppose you can do it. All right, let's talk a little bit about PathMTU and PathMTU discovery, right? This goes back to us saying that in IPv6, there's no more fragmentation permitted along the path. This also ties directly in to what we do in IPv4 for efficiency is PathMTU discovery, which is the same process in IPv4 and IPv6. So just some terms first, right? MTU, are you familiar with MTU? It's just the maximum size packet that we can have on any particular link. We have this concept of PathMTU, which just means the MTU from wherever the source of the traffic is to wherever the destination is. So we're talking about the largest common denominator, basically, right? The largest packet that we can send across that path. So it's the smallest of the MTUs across the path. Now today in the internet, this is almost always 1,500 bytes because almost everybody's using Ethernet for almost everything these days. But there are some exceptions to that. There are cases where we're using a lot of VLAN tags, for example, that use up the space that's allocated VLAN tags to make your Ethernet MTU slightly smaller. This happens more often in places where you're using some sort of technology like MPLS or something to carry multiple VLAN tags across multiple networks. And when you have all these different tags and headers and that sort of stuff tacked onto a packet, sometimes you can end up with a packet that's less than 1,500 bytes. Regardless of how we get there, the concept is really important, and I want to go through that a little bit. So, and again, this works the same way in IPv4 as it does in IPv6, but it's a really important concept. So PathMTU discovery means that we're going to find the maximum size packet that we can send across that particular path. So in this case, we're starting with an MTU, the first link here from the source of 1,500 bytes, say it's an Ethernet, and the same thing with the second link. So what we do is we start by sending a packet. Let's say we've already completed the TCP handshake. Maybe this is a web server trying to send out a web page that has a lot of data on it. So that first packet, the device already knows that its first hop MTU is 1,500 bytes, so it sends that 1,500 byte packet towards the destination. Gets the first hop. The first hop here says, no problem, my next link is also 1,500 bytes MTU, so I have a 1,500 byte MTU packet, I just forward it on to the second router. But that second router is where we run into a problem. The second router has, all right, I have a 1,500 byte packet, but my next MTU is 1,400 bytes. Again, maybe there's a bunch of VLAN tags or something on there that's reducing that MTU size. In IPv4, before PathMTU discovery, we would just take that packet, maybe break it into 2 packets, and then just forward on the 2 packets. Again, that's inefficient for a lot of reasons. First of all, this router has to take time to fragment that packet. Second of all, now we have 2 packets for the rest of the network processes at once. Now we've doubled the load on the rest of the network. Remember, the load on a network is mostly based on the number of packets, not based on the size of the packets. All right, so as long as we're using PathMTU discovery, this router says, I can't forward that packet, it's too big. So this guy sends a message back to the source saying, packet too big, my next hop MTU is 1,400 bytes, not 1,500 bytes. So the source of that packet receives that ICMP message. He goes, okay, no problem, I'll send a 1,400 byte packet instead of a 1,500 byte packet. That's what we see here. Packets of 1,400 byte MTU get sent. First hop, no problem. Second hop, now that's no problem, says my next hop is 1,400 bytes. Third hop, now we have a problem. Because that last link there is only a 1,300 byte MTU. So the same process occurs again. That router sends a message back to the source saying, that packet's too big, I need a 1,300 byte packet or smaller. Same process again, source now sends a 1,300 byte packet, and that packet will make it all the way to the destination because it's below the path MTU. All right, make sense? Yes?
Then what happens when you're sending these packets and they're taking different paths because that's how dynamic routing works?
Well, but to any one particular destination, the path should be similar each time. Unless, the only exception to that would be is if you're in a case where you're doing equal cost path load balancing. And so when you create equal cost path load balancing situations, you generally want to make sure that each one of those links in that bundle have the same MTU. And it's almost always Ethernet anyway, so it's usually not a problem. But let's say that there was a problem. But what happened is, maybe that first 1,500 byte packet makes it all the way to the end. But maybe the second one gets loaded onto a different link that's 1,400 bytes, it would get that message back and it would start sending 1,400 byte packets. So while those packets might get load balanced back onto the 1500 byte, they would still work. They would just be slightly less efficient. So it would still work, but generally that's a pretty corner case. It doesn't really happen very much. The bigger problem, if you're anticipating where the problems run into this process, is let's say that this wasn't just a router but a firewall. And let's say that some security administrator mistakenly blocked all inbound ICMP on that firewall. Notice I said mistakenly.
No.
Don't do that.
That
So
wouldn't happen.
if you block all ICMP on this, because a lot of people think, oh, ICMP, I don't need any of that coming to my network. It gives hackers some sort of hole in my network. I'm not sure what it is. If you're blocking all ICMP, those ICMP messages are not going to make it to the source. The source will never know to send a smaller than 1500 byte packet, but that packet's going to keep getting dropped there. So now the TCP handshake works, right? Because those are all little packets. They all make it through across the whole network. SYN, SYNAC, all that stuff, right? So your TCP connection establishes, but the data packets never make it through. So how many people have loaded up a web browser on like some terrible network somewhere, and it looks like it connects, but it just sits there and loads forever? That is a symptom, a possible symptom of path-empty discovery problems. There could be other problems too, of course, but oftentimes that's the problem here is because the source blocked that. And some large internet properties have made that mistake in the past. I know for a fact that Yahoo was doing that quite some time. This was back again in the early 2000s, but it could be a real problem. And now in IPv4, we would often fix that problem by just going to this router and say, we'll just fragment the packets. Even though we have no fragments set, maybe we're telling the network not to fragment, just ignore that fragmentation. Well, technically in IPv6, you're not allowed to do that. And that's why this is an even more important issue in IPv6 than it was in IPv4. So, our advice is never block all ICMP. Sure, you can block parts of ICMP that you don't need, but you need to carefully look at what ICMP is allowed, what isn't, and make sure that you're properly protecting yourself, but not hurting yourself from issues like this. So, we'll talk about QoS just a little bit. Like I mentioned before, the 8-bit traffic class field is just diffcert. It works exactly the same. People using diffcert today, using diffcert code points like EF and AF and everything. Okay. Some folks use it, some don't. Obviously there are parts of those 8 bits that you would use to prioritize some traffic over others. You might say voice traffic gets highest priority because I just want to make sure my voice quality stays up. Someone starts doing a data download at the same time, and I want my voice quality to suffer, so you might give voice, for example, a priority. So those 8 bits work the same. There's some standardized treatments for that, whether it's assured forwarding or best effort or whatever. But it's all defined for IPv4, and it's exactly the same for IPv6. So if you've done it, then you know it's the same. What's more important in IPv6 that's different is this flow label that we talked about just a little bit earlier. The whole idea of the flow label is to make it clear to the network and maybe even network analytics what packets are part of the same flow. And by flow, we generally mean, in IPv4, what we generally mean is packets that are all part of the same source destination pair and usually the same source destination port. But in IPv6, we can be more flexible because it's the source that determines what flow label to put on packets. So by definition, the flow state expires after 120 seconds by default. So every 120 seconds, that flow label would reset. And it's defined to be unique from as long as you're looking at a particular source. And so the label itself is unimportant. It's basically a pseudo-random number to just identify that flow. But the idea is that if you're used to things like NetFlow today that try to determine what packets are part of the same flow and give you statistics about how much traffic is being sent and received between different sources and destinations of the network, this is supposed to make that a little bit easier. Now, there's not a whole lot of implementation of that yet, but it is a standardized field in the IPv6 header, so you can look at it. If it's set to 0, you know that that packet either doesn't belong to a flow or the source just doesn't set the flow label. And we're not seeing a lot of sources setting these flow labels yet, but again, it's part of the protocol. And hopefully, we'd like to see some applications come out of this in the future.
Just a quick question.
Yeah.
On the flow label.
Yes.
You start saying when I hear flow labels, I think APIs. This is something distinctly different.
distinctly different from MPLS, right? It's not an MPLS label, it's a flow label. So an MPLS, a label is used to identify packets that are treated across the network as part of a LSP, a label switch packet. This is not that. That would be an additional MPLS header that would go before the IPv6 header if you're running MPLS. It would have the flow label. It would have the MPLS label in it. I'm going to step on my own tongue.
So this is, so I know this is probably different here, but this has nothing to do with any kind of quality of service, any kind of routing or anything like that. It's strictly like putting in.
It's strictly to identify a flow. Now, you can imagine using it for quality of service purposes. You could say that anything in this flow, once I've identified that this flow should be treated with a higher priority, maybe I use the flow label to identify additional traffic that should be treated as higher QoS.
But where do you do the identification? Is that done? Is that done at the end? It can't be done at the end. It would have to be done somewhere along the route.
Well, the flow label itself is just arbitrary set by the source, right? So if you were also setting a QoS, for example, that at the source, maybe differentiate again maybe between voice traffic and lower priority traffic. You might use that plus a flow label to identify a particular flow of voice traffic, for example. This is all in theory, right? There's no implementations of anything like that. Today it's just an arbitrary number that no one's really using. All right, let's talk a little bit about how IPv6 addresses are put together. Like we mentioned, it's 128-bit address space. That's 2 to the 128th addresses, or 3.4 times 10 to the 38, not 340 undisclosed addresses. Huge address space. And the whole idea that I want to get across when we talk about the address space is that because it is so vast, it gives us a lot more flexibility in how to use the addresses to make it easier on us as humans to manage the network. So we can create hierarchy to make it easier for us to identify what's going on in the network. And like I mentioned before, by standard, half of the address is used for network, and the other half is used for host identification. So the last 64 bits, standardized, should be the host address on the way. Again, so easier to manage, easier when you have to do auto configuration. As a matter of fact, auto configuration only works when you use a /64, when you use those 64 bits the way I'm describing. So everybody remember your hex? Like, don't need to go through this, we don't have a lot of time. So just real quick, hexadecimal, right? It's just a numbering base with 16 instead of 10 values in it. And so after we get to 9, we just go A, B, C, D. So address syntax, right? So the top is, oops, wrong button. So the top is just a binary representation of IPv6 address. Obviously, as humans, we can't read this. Computers are great at that, but we're not so good at reading that. I can't read that very well. So to make it easier for us to read, first we divided it into 16-bit boundaries, right? In IPv4, we did 8-bit boundaries. Much bigger address, we're doing 16-bit boundaries. Then we take each one of those 16-bit blocks and convert it to hexadecimal. So that looks like this. We can then drop leading zeros from each one of those blocks, again, just to make it easier to read. So in this example, right, we've dropped the 0 before the DB8, and this block of zeros we just dropped down to just a single 0. Again, we're making it a little bit easier to read, making it shorter. And as humans, we tend to pick addresses with a lot of zeros in them because it's just easier for us to think about. So we tend to be able to compress addresses quite a bit. So there's another step to that, where we can compress even contiguous strings of zeros in each hextet. That's the unit that goes in between each colon, hextet, hextet, hextet. Where if there's a contiguous string of zeros in contiguous hextets, we can replace that with just a double colon. So now this should look a little more familiar if you've ever looked at like an interface configuration that is enabled for IPv6. You're almost always going to see an FE80 address like that. That's a linked local address. We'll talk about that, what that means in a minute. But suffice it to say, the representation for us as humans, this is a heck of a lot easier to read, certainly than this, but even easier than this, right? Much shorter, much more concise. What's important though is that we can't drop zeros that are part of a different hextet, right? So in this case, FF02 colon 30 and then followed by these zeros cannot be FF02 colon 3 colon 1, right? Because we don't know that there's a 0 at the end of that group, right? So we can drop leading zeros, we can't drop trailing zeros within a hextet. does become this, which is nice and short.
I did have a question.
Yes.
Going back to that, how do you know if you drop in like 6 different sets of zeros, how do you know where it takes back up? It comes from-
You can only drop, you can only have a double colon once.
That's what I was trying to do.
By standard, right?
Only one bit.
Right. And so you know there's going to be 8 sections of 8 hex sets, and you know that, so you know that that's how many zeros to add on. Right? You can only do it once, and the standard says you're supposed to drop the longest one, and if there are multiples that are the same length that are the longest ones, then you're supposed to drop the first one. Most devices are smart enough to be able to figure out what you really meant, even if you don't drop quite the exact right ones, but you can still only do it once, or you'll get an error.
It counts from the beginning and it counts from the back. So if you have 3 at the beginning and 2 at the end, and you know there's something in the middle that has to have. That's what I understood is how it works.
Representation of prefixes of subnet addresses. In IPv6, that's standardized on this CIDR format, the slash format that we've gotten used to in IPv4, but some devices, for some reason, even these days, insist on the old mask format where you go 255.255.255.0. That's not allowed anywhere in IPv6. There's some times where you might want to think about it that way, but the representation standard is always used for the slash notation. So just real quick, after the slash, that number always represents the number of network digits in the address. So when you say /64, I'm just saying the first 64 bits are the network address, the last 64 bits are the host address. If I'm saying /48, the first 48 bits are the network address, and the last chunk of addresses are not important. So /48s tend to be a kind of a typical subnet that you see in the internet to represent a site. It's very loosely defined. When you design your addressing plan, you kind of define it however you want. But a /48 generally represents a site. A /64 is generally a single broadcast domain, a single LAN. And you generally don't want to use longer prefixes than that. There's a couple exceptions here for like point-to-point links or router loopbacks, or if I use a 127 or 128. We give everyone the advice, though, that if you do that, to reserve that whole 64, so that if someday you need to expand that address up to a /64, you can without having to renumber stuff. Again, the address space is so big, even though that seems a little wasteful, it really might save you a lot of time in the future. Excuse me. So again, I thought I fixed that. That should be a 64. So again, you know, just typically in the internet, you might see the first, and this is typical but not required. You might see the first 48 bits to be the internet routing prefix. You might see in the global BGP table for how to get to a particular site. That could also be a /32. That could be a /28. But generally, it's going to be 48 or shorter of a prefix, right? The next 16 bits, or whatever those numbers are, is generally kind of your local subnet ID. So if I have a /48, say, for this hotel, I might then use the next 16 bits to identify particular LANs within this hotel. Well, the last 64, I don't know why that says 62, the last 64, again, is the interface ID by standard. And then just, if you did want to kind of look at what a representation in a mask format might be, of what a /48 or something like that, it might look like this, you know, walks through the mask. But again, we don't use that representation on IPv6. So when we build an addressing plan for IPv6, we want to think more carefully about how we use the address space and how us as humans can better understand what's going on than in what we're used to in IPv4, where most of us have to be very, very conservative in how we use address space because it's running out. So in IPv6, we can think about things like documentation, and about sequence, and about aggregation, and about geography instead of necessarily just network topology in order to build our addressing plan. So we can do things like use parts of the address to identify a function, or a security zone, or geography. We have just a couple examples here of that, just so you can get the concept. So let's go back to that example where our allocation from the RRR is a /48. So we're going to use basically these next four digits in the hextet to represent things. In this case, we're picking this A here as part of this /52 to just represent our location. So by picking a single nibble, right, that's 4 bits, we get 16 values, right? Single digit in hexadecimal equals 16 values, right? So if we use that digit to represent a location, and let's just in our example, we have a campus with 9 locations, let's say. We can use that, and we have up to 16 locations. We have 9 plus another 7 if we need them in the future. Let's say then we want to identify a function within that location. Let's say it's like a security zone, or one subnet for servers in each building, and one subnet for voice in each building, one subnet for backups, whatever we want it to do. We could use that B, and now we get another 16 bits, or rather another 16 functions, 4 bits, to represent a function within that location. So now we have location, and now we have function within that location. And then let's say we choose to use the next 2 bits, or rather the next two nibbles, or 8 bits, for our local subnets in that location. So now we have that gives us 256 subnets per location. So that's huge, right? In a typical campus of some sort of 9 locations, and that have within those 9 locations have another 16 possible functions. And within each of those functions, 256 networks that we can use. Generally, in a lot of places, that would be enough. But you can allocate this however you want. This is just kind of an example of how you might use the address space to identify things within your network to make it easier for us to do. The routers, the switches, they don't care, but we do because it's easier for us to identify them. So now, if you did this, you could look at the address and go, oh, well, there's a 1 in this column and a C in that column. Then we instantly know, oh, that's the headquarters building, and that's the voice network. Now I know instantly what network I'm looking at without even necessarily having to look it up. So that makes our documentation easier, it makes it easier for us to troubleshoot and identify what's going on. And you can arbitrarily make that however you want. That's again just one example. To your point earlier, we're no longer limited to our typical rule of thumb of 254 devices in a particular subnet because we're not using the /24 and IPv4. The addressing itself provides no real limitation to how many devices we put in a network. Again, for performance reasons and for management reasons, we're still going to want to limit how many devices we put in a single broadcast domain. But as far as IPv6 is concerned, it doesn't care. Put as many as you want, up to a /64, which is every Ethernet device ever invented, plus 2 to the 4, right? So it's really not a problem. Or times 2 to the 4. We can use all 1s and all 0s networks. You know, back in IPv4, that's supposed to go away, but there's still a lot of legacy equipment out there that freaks out if you have all 1s or all 0s as either the network number or the host is still defined as broadcast. But that doesn't exist in IPv6. There is no broadcast in IPv6. We've eliminated the whole concept of secondary subnets. Like I said before, it's very typical for an IPv6 interface to have more than one address on it, and none of them are necessarily secondary or primary. They can be, for various purposes, used first or second or something like that, but they have different purposes, and they're all expected to be used. One important thing to keep in mind, though, right, is that with a much larger address space and a much more flexibility about how we create subnets, there's a danger that we can create too many subnets for our devices and have routing tables that are too enormous. So when we do design our addressing plan, we need to be careful to make sure that we're still aggregatable. That's why that example before, where we're talking about geography as the first digit and then function and subnets as the second 2 categories there, is usually better because usually you're going to have one device in the building that's routing traffic for that entire building, so you can send one route for that /52 in that example out to the rest of your backbone instead of a couple hundred routes for all the different functions and subnets within the building. But in your case, you may do something different. You may have a building where, because of security reasons, you have multiple networks that don't actually touch each other within the building and have separate exits. In that case, geography might not be the best way to do that because you want to be able to aggregate those addresses. So address types in IPv6, there's basically 3. There's unicast addresses. So unicast means the same thing it does in IPv4, where an address exists usually on a single interface, and traffic is delivered to that single interface. There are anycast addresses, which exists in IPv4, but was never really truly standardized, but it is a lot more standardized in IPv6. Where an anycast address means that there's a whole different bunch of interfaces with the same address, and the network is designed to deliver the packet to the topologically closest interface with that address. This is used a lot in IPv4 and in IPv6 now for things like DNS. A lot of the root DNS servers are anycasted, where there's a single address and the network just automatically directs traffic to the nearest one. If you've ever used the Google 8.8.8.8 address, there's not just one device in one place with 8.8.8.8 on it. If you do a trace route to it from wherever you travel to, you'll see that there's usually only 3 or 4 miles to get there, no matter what part of the world you're in. And that's because it's anycast. They have local servers in hundreds of locations around the world, all sharing that 8.8.8.8 address, and so the network just directs that traffic to the nearest interface. Same thing in IPv6, same concept. And Google actually has that IPv6 anycast DNS address as well. And then multicast, which we did standardize in IPv4, means I'm going to send a packet, and that packet is going to get delivered to multiple interfaces. So copies of that packet are made so that that same packet is delivered to multiple interfaces with that same multicast packets. I mentioned before, there's no more broadcast in IPv6. Everything that we used to do with broadcast in IPv6 has been re-implemented using multicast in IPv6. And the reason for that is it's just much more efficient. There's almost never a reason that every device should get a copy of the same packet. Usually there's a way to narrow down what devices should have to process that packet. So we use multicast instead of broadcast, and we're all familiar with a lot of the attacks that used to happen with broadcast addresses as well.
Is there any push to get more toward unicast, like say all government computers will be on this IP set range and all of this? You know what I'm saying? Is there like a standardized word unicast to be?
Well, not really like that. I mean, you would go and request IPv6 addresses for your purposes, and those would be yours to do with however you want, right? And most a lot of networks already have those, but not as far as real limited like that, where it's a particular sign block. You would have to look at it. Yes.
So we don't have broadcast addresses anymore, no more broadcasting, but we still have the concept of broadcast domain.
So remember the layers, right? So broadcast domain, we're talking about layer 2, right? So Ethernet is unchanged. That's still the same. So even though you may send a multicast in IPv6, that still might be implemented as a broadcast at layer 2, depending on a lot of factors about how that's set up. So layer 2 still has broadcast, but you don't have broadcast across the IPv6 domain. So I can't remember there was that. Remember the Smurf attack, the directed broadcast attack in IPv4? We pretty much eliminated that back in the late 90s, but there used to be that if you had, let's say, a /24, 1.2.3/24, you could send a packet to 1.2.3.255, and that would duplicate that packet to every device on that /24. People were using that as an attack, because what I could do is spoof my source address, send traffic to these broadcast addresses, and my one packet would turn into 100 packets, and those would all get sent to that smooth source, and if I did that a few times to a few different places, I could inundate someone with traffic. So there's no way to do that in IPv6 because there's no way to specify a broadcast IPv6 address. But at layer 2, that's still different. Layer 2, the Ethernet still works the same way it does, but there would be no way to do that from outside of the network. So within unicast addresses, we have a few subtypes. We have global unicast. Global unicast always starts with binary digits of 001. Global unicast does what the name implies it does, which means it's just a unique address in the entire internet. A global unicast address is assigned to you by some entity that eventually reports up to the ITF, or the IANA, if you want to be specific. So most cases, people will get those from the upstream service provider. In some cases, people will get those from the regional internet registry. But global unique address is always assigned to you by some upstream authority because it's important to keep those unique, and you're guaranteed that that's unique in the world. So again, the structure is again, this is kind of recommended, but not necessarily a rule. In this case, we're showing the 45 bits after the 001 is your global routing prefix, and then those 16 bits of subnet ID. Remember, I mentioned this could be a slash instead of a 48. This could be a /32. This could be a /28. It just depends on the size block that you've been assigned by your upstream provider or by your regional internet registry. Unicast link local addresses. So the link local addresses are automatically locally generated when you enable an interface for IPv6. And we'll talk about a little bit about how it does that, but it always starts with this prefix, which is this in binary, but it comes out with FE80, FE80::. And it's always defined as a /64. So basically what we're doing here is, since this is well known, FE80, every device that has an IPv6 stack in it knows that FE80 is a link local address, and then it can use a process on the Ethernet MAC address to create a unique interface ID. We'll talk about that. Because link local addresses are not globally unique, when you're sitting on your local device and you have more than one interface, which a lot of devices do, you have to have some other way of identifying which interface I'm talking about. So let's say if I wanted to ping this address, I have to tell my operating system which interface I want that traffic to go out, because each layer 2 network is its own link local domain. So we have the standard of using the % sign followed by an arbitrary string to identify an interface. So in most Microsoft products, they're usually just sequentially numbered, so that's why we show a 3 here. It's usually just 1, 2, 3, whatever comes up first. In most Unix-like operating systems, that's usually the alphanumeric identifier for the interface, usually like ETH0 or EN0 or something like that. But it's arbitrary based on the operating system. The important point is when you see that percent indicator, that's trying to show you what interface we're talking about, and that's only important locally on your local device, not necessarily globally. Okay, we also have unique local addresses. Unique local addresses is more similar to RFC 1918 private address space, or your 10 network, or 192.168, or that sort of stuff. In IPv6, there's only one, and it's this prefix FD00::/8. In binary, that's this representation here. And that's a /8 for you to do basically with whatever you want. Now, there's a lot of debate about whether whether you should use this or not. I recommend that you do not use EULA addresses or unique local addresses. The reason is that IPv6 address space is so big, it's very, very easy to get additional global unique address space. And you can simply define a chunk of your global unique address space as address space you're not routing outside of your local entity and just not allow it through your borders. The reason I recommend doing it that way instead of using these unique local addresses is that if you ever have to merge with some other organization, or if some other organization, someday you decide, actually, even though I blocked this from outside, now I need to let them in to talk to a couple of unique devices, you can still, with a network configuration change, allow that communication to happen without having to go renumber your whole network to remove conflicts with address space. So some people make the counter argument that, well, I like using unique local addresses because if someone misconfigures my network, I know that those addresses will never be exposed outside because no one else will listen to them. I argue back, if you have the capability of misconfiguring your network that badly, you have much bigger problems, and this isn't the issue that you should be dealing with. But that's the debate on that issue. There is a process that you're supposed to go through so that if you do use unique local addresses, that you have a high chance of it being an actual random one, so that if you did have to merge with some other organization, there's less of a chance of overlap between you and some other organization. I suspect a lot of people don't actually follow the proper process and just arbitrarily pick a number. But you don't want to do that because as humans, we're bad at picking random numbers. So if you're going to use unique local addresses, please look up the proper process to generate one so that you get a truly random one instead of risking overlapping with somebody else's. Anycast, we mentioned Anycast. Anycast is really not a specific type of address. You can use any address as an Anycast address simply by assigning it to multiple interfaces. And the networks, the internet networks naturally do this Anycast thing. If I advertise the same address in 5 different places around the world, the network will automatically just pick the best path. So there's not really any magic to Anycast. It's a pretty useful tool. The big thing to keep in mind if you do use Anycast, though, is that you don't want to use Anycast for long-lived sessions, because if a route changes in the internet, the actual destination of your traffic could change. So it's good for things like DNS that are short-lived, very transactional type protocols. Some people use it a little bit for even some web service type stuff that's at least short, small objects. You don't want to use it for long-lived sessions, though, because as soon as the route changes, you can disrupt your whole TCP session.
Brandon, we're about 5 minutes over. If you want to.
Oh, okay. All right, multicast we've talked about a little bit. It has this start FF02 and FF01. Let's go to real quick here a couple other things that I wanted to get to. So I mentioned how the link local works by converting your MAC address. We use this process called UI64. So let's say that this was your 48-bit Ethernet MAC address. To convert that into that last 64 bits of that link local address, and there's a lot of archaic reasons here, but basically what we do is we split that address down the middle, and we insert FFFE in the middle, and then we flip this one universal bit that's in this position here. So your Ethernet MAC address always starts with 00, but when you do this UI64 process, it turns to 02. And then, I have press on there. And then we have this UI64 address, which we can then add that FE80 : to the beginning of, and that is our unique local address, or the unique linked local address. Pretty simple process, but that's how we do this automatic bootstrapping thing in IPv6, where we can get on a network and we can even communicate across the network without having any external server, any DHCP server, anything like that. And the reason I like to mention this especially is that if you have a network today that's not specifically blocking IPv6 but doesn't necessarily enable for IPv6, you probably have a lot of communication happening over that network over IPv6 anyway on local LAN segments, because most protocols will prefer IPv6 first. And so as long as it's local and has some way to learn another linked local address, it's able to just go ahead and communicate over that linked local address without actually going on IPv4. So in interest of time here, I'm just going to flip down here. I knew we'd only make it about halfway through, but I want to leave a little bit of time for questions, which I didn't.
He will be available at the Walker booth for any questions.
Yes. So, and like I said, this is just a small part of our much larger IPv6 training class, which there was only 100 slides in this presentation. There's like, I don't know, like 400 or 500 in the full class. In the full class, we talk a little bit more about how the whole bootstrapping process works. There's a couple different options between what's called stateless auto configuration, which just means I'm using the same UI64 process along with a router advertisement that gives me a globally unique prefix. And then there's a DHCP-based process too, which we're a lot more used to. But the important point again being that you still need a DHCP server in order to bootstrap devices onto your network. So as long as you have a router that supports IPv6, you can configure your network for IPv6 without any external. There's a lot of reasons you might want to use a DHCP server, but you don't have to. So we'll stop there unless there's any other questions.